Welcome back. Let's look at some examples involving vectors in 3D. All right, so here's our first example. For the given vector below, we want to find the position vector and its magnitude. All right, so we have a 3D graph here with a vector v, and it has an initial point A at the point 3, 1, negative 2, and a terminal point B at the point negative 3, 4, 4. And so what we want to do, given this vector and its initial and terminal points, is find the corresponding position vector, the version of this vector where the initial point would be the origin. All right, and to find the position vector, what we need to do is take the difference in the x-coordinates, the y-coordinates, and the z-coordinates between our initial and terminal points. Now, as a reminder, this point is the initial point because it's where the vector begins. It's heading in this direction. We know that because of this arrow. It's pointing towards this point, which is the terminal point because it's where the vector ends. It's the point the vector is pointing towards. All right, and so when we find the difference in our x, y, and z coordinates, we subtract the coordinates of the initial point from the coordinates of the terminal point. All right, and those will create the x, y, and z components of our position vector, vector v. So let's do that. Let's start by taking the difference of our x coordinates. We'll have negative 3 minus 3. So let's write that down. Negative 3 minus 3. That will make up our x component. Then for the y component, we'll take the difference of our y coordinates. So we'll have 4 minus 1. All right, 4 minus 1. And then for the z component, our third component, we will take the difference of our z coordinates. So we'll have 4 minus negative 2. All right, so 4 minus negative 2. Okay, so now if we simplify, this will be equal to the position vector of the point negative 6, 3, 6. Right, negative 3 minus 3 is negative 6, 4 minus 1 is 3, and 4 minus negative 2, those negatives cancel out, so we have 4 plus 2, which is 6. And so this answers the first part of this question. Vector v is the position vector of the point negative 6, 3, 6. So what that means is if we plotted this position vector, it would have an initial point at the origin at the point 0, 0, 0, and it would have a terminal point of negative 6, 3, 6. Okay, but that's not everything we wanted to find. We also need to find the magnitude of this position vector. And in order to find the magnitude, which by the way is the same thing as the length of our vector is the magnitude. In order to find that, what we need to do is take the square root of the sum of our components squared, right? For a position vector, the magnitude is equal to the square root of v1 squared plus v2 squared plus v3 squared, where v1 is the x component, v2 is the y component, and v3 is the z component. So in this case, this will be equal to the square root of negative 6 squared plus 3 squared plus 6 squared. Now, negative 6 squared is 36, 3 squared is 9, and positive 6 squared is 36. So this is equal to the square root of 36 plus 9 plus 36. And 36 plus 36 is 72, plus 9 is 81. So this will be equal to the square root of 81, which is a perfect square. We know that the square root of 81 is 9, so this is equal to 9. And so 9 is the magnitude of this position vector, vector v. Okay, let's take a look at a different example. All right, so for our next example, we want to write the following vectors in standard unit vector notation. Another way that you might hear that called is writing it as a linear combination of unit vectors I, j, and k. All right, now remember, I, j, and k are the standard unit vectors for the x, y, and z directions. Vector I is equal to the position vector of the point 1, 0, 0. Vector j is equal to the position vector of the point 0, 1, 0. And vector k is the position vector of the point 0, 0, 1. And so vector I represents the x direction, vector j represents the y direction, and vector k represents the z direction. And so what we can do to rewrite these vectors is multiply the x components by vector I, then add that to the y components multiplied by vector j, and then add that to the z components multiplied by vector k. And that will give us another way to represent these same vectors. All right, and so let's start with the first one here. Vector A will be equal to 3, the x component multiplied by the standard unit vector in the x direction, which is I. So we'll multiply it by I, then we'll add that to the y component, which is -5. So actually we will subtract this. We'll have -5 times the standard unit vector for the y direction, which is j. So we'll have vector j, and then we'll add that to the z component of 8 multiplied by the standard unit vector for the z direction, which is k. So we'll multiply 8 by k. All right, and so that is an equivalent way of expressing vector A. Whether you write it this way or this way, they both represent the same vector. Now, if you're not convinced, let me just quickly show you why this is true, and then we'll go ahead and do these other two vectors. But if you multiplied 3 by vector I, you'd be performing scalar multiplication. You'd be multiplying this 3 by all three of these components. So you would have 3 times 1, then 3 times 0, and 3 times 0. That would give you the vector of 3, 0, 0. And then for this vector, we have -5 times j. So you're multiplying -5 by these three components. So you'll have 0, -5, and 0. So we would be adding this vector, 0, -5, 0, and then you'd be adding the vector of 8 times k. So we're multiplying 8 by each of these components. So you'd have 0, 0, 8. 8 times 0 is 0, and 8 times 1 is 8. So now if you add these three vectors together using vector addition, you would be adding the x components together. So 3 plus 0 is 3, so that gives us the x component. Then we'd add the y components together. 0 plus -5 plus 0 is -5, our y component, and 0 plus 8 is 8. That's our z component. And so that's why this is an equivalent way of expressing this vector. It's just a way of writing our vector such that we are working with terms rather than this regular vector notation for the position vector of a particular point. All right, sometimes it's just going to be easier for us to work with a vector in this form as compared to this form. So being able to switch back and forth between these notations or these forms is an important part of Calculus 3. All right, so now let's work on the other two vectors. In fact, if you'd like, I would encourage you to pause the video and try and see if you can rewrite these vectors in standard unit vector notation yourself first, and then play the video and see if you get the same answers that I do. All right, so I'll give you a second to pause the video, but now I'm going to get started and write vector B in standard unit vector notation. So here's what that will look like. This will be equal to that x component of 2 multiplied by the standard unit vector for the x direction, which is I, and then we're going to add that to our y component of 0, so we'll have 0 times the standard unit vector for the y direction, which is j, and 0 times j is actually just going to be 0, so we'll simplify that then. But let's just write our last term here, which will be to add -10 times the standard unit vector for the z direction, because -10 is our z component. So we'll have -10 times k, which is our standard unit vector for the z direction. All right, but now we can simplify this. Since 0 times j is just going to be 0, we can completely omit that from our answer and just write that our vector is 2 times I minus 10 times k. All right, and that is an equivalent form of this vector. Both this notation and this notation represent the same vector, which is vector B. Okay, now let's look at our last vector here, vector C. Vector C is the position vector of the point 0, 0, -7. So maybe you can see this and just very quickly determine that the standard unit vector notation of this is not going to have an I or j term. It's just going to have -7 times k. But if you don't see that right away, it's okay. Here's what I'm talking about. This will be equal to 0 times vector I, right? The x component times the standard unit vector for the x direction. Then we'll add that to another 0 times j, right? We have the y component times the standard unit vector for the y direction. And then our z component is -7. So we'll have -7 times the standard unit vector in the z direction, which is k. And so we have -7 times k. But now 0 times I is 0, and 0 times j is 0, so we can cross out those terms, and all we're left with is -7 times k. That right there is the same as this vector right here. They both represent vector C. Okay, and so now that's it for this example. We have now successfully rewritten these three vectors in standard unit vector notation. Next up, we want to determine which of the following vectors are parallel to vector v, which is the position vector of the point 3, 2, negative 5. All right, so now, in order to solve this problem, you have to understand what it means for a vector to be parallel to another vector. Well, when you're working with vectors in 3D, the way that you can determine if they are parallel is by showing that the vectors are scalar multiples, right? So for these four vectors, vector A, vector B, vector C, and vector D, what we want to do to determine if they are parallel to vector V is see if we can pull out some scalar multiple out of each of those components such that we will have a scalar multiple multiplied by vector V. All right, and so let me show you what I mean. Let's start with vector A here. Notice that these three components, negative 6, negative 4, and 10, are all divisible by 2. We can pull out a common factor of 2. If we do that, this will be equal to 2 times the vector of negative 3, negative 2, comma 5, right? If you multiply that 2 back through, 2 times negative 3 is negative 6, 2 times negative 2 is negative 4, and 2 times 5 is 10. We just divided each of those components by 2. And look at the vector that we have left here. We have 2 times a vector of negative 3, negative 2, 5. Notice that this vector is almost the same thing as vector v, except those components are the negative version of those components. So that leads me to believe that if we pulled out a negative 1 from this vector, so we'd have negative 2 as our scalar multiple, then the vector we're left with would be vector v, and so vector A is a scalar multiple of vector v. And so let me show you what I mean. If we pull out negative 1 from each of these components, this will be equal to negative 2 times positive 3, comma positive 2, comma negative 5, and that is the same exact vector as vector v. So vector A is equal to negative 2 times vector v, which means that vector A is a scalar multiple of vector v. All right, and so because that is true, because vector A and vector v are scalar multiples, we can conclude that they are parallel, that they have the same direction. All right, so let's write that down. We can conclude that vector A is parallel to vector v. All right, now we have 3 more vectors to work with to see if they are scalar multiples of vector v. And if you want to challenge yourself, feel free to pause the video and see if you can determine which of these vectors are parallel to vector v on your own. And then when you feel like you're done, you can play the video again and see if you get the same answers that I do. Okay, but now I'm going to move on to vector b here. To show if vector b is parallel to vector v, once again, I'm just going to start by pulling out some kind of a common factor. And so what can I pull out of these 3 components? Well, first of all, I see that these 2 components are being divided by 3, so I'm tempted to pull out a 1/3 out of these 3 components. We'll see if that helps us at all here. So I'm going to start with that. We're going to divide each of these terms by 1/3. Now, it's going to be a little bit tricky for this first term here. 2 divided by 1/3, right? If we write 2 divided by 1/3, remember that dividing by a fraction is the same as multiplying by its reciprocal. So this is equal to 2 times 3. The reciprocal of 1/3 is 3, because you'd have 3 divided by 1, which is 3. And so 2 times 3 is 6, which means that 2 divided by 1/3 is 6. All right, so if we pull out 1/3, that first component will be 6, and then we'll have 4 and negative 10, right? 4/3 divided by 1/3 leaves you with 4, and negative 10/3 divided by 1/3 leaves you with negative 10. And now we don't have a vector that looks like vector v yet, but I actually see another factor that we can pull out. 6, 4, and negative 10 are all divisible by 2. So let's pull that out. If we do that, this will be equal to 2/3 times our vector, right? If we pull out 2 from these components, we'll have 2 times 1/3, which is 2/3, and we'll be left with 3, 2, negative 5. 6 divided by 2 is 3, 4 divided by 2 is 2, and negative 10 divided by 2 is negative 5. And if you look at our result here, we have 2/3 times the position vector of the point 3, 2, negative 5, which is the exact same as vector v. So vector b is equal to 2/3 times vector v, which means that it is a scalar multiple of vector v, and so vector b is parallel to vector v. They have the same direction. Okay, so that's it for vector b. Let's move on to our next vector. This time we have vector c, which is equal to 6i plus 4j plus 10k. All right, now to easily compare this notation to vector v, let's rewrite this vector into standard unit vector notation. It will be equal to 3i plus 2j minus 5k. Okay, now comparing these terms to these terms, what do you notice that is a little bit jarring? Well, these three terms, or these three components of vector c, are all positive, but for vector v, two of them are positive and one is negative. So what that means is if we were to pull out a scalar multiple out of these three terms, there's no scalar multiple that we can pull out that will keep these first two terms positive and make the third one negative, right? If we pull out a negative scalar from these terms, we're pulling out that negative from all three of them. We can't just isolate one. We have to pull out that negative from all three terms. So if we try to make that last term negative such that this was a scalar multiple of this, it would be impossible because we would make these two terms negative in the process. And so just based on that alone, the fact that we can't match the signs of these terms to these terms, we can conclude immediately that these two vectors are not going to be parallel. All right, and so we can conclude that vector c is not parallel to vector v. All right, so I'll write not parallel to vector v. Okay, now let's look at our last vector here, which is vector d. And this is going to be a very similar case to what happened with vector c. Notice that our terms are positive, negative, positive, but the terms for vector v are positive, positive, negative. They are not exact opposites of each other, right? If you looked at vector a, the first two terms were negative, the last one was positive. That's the opposite of vector v. The first two were positive, the last one was negative. So pulling out a negative from those terms made it such that vector a was a scalar multiple of vector v. But in this case, that's not the opposite. We have a positive term, a negative term, and then another positive term. The opposite of that would be negative, positive, negative, not positive, positive, negative. All right, I hope that makes sense. It's going to be impossible for us to pull out a scalar multiple from these terms such that we change these signs to match these signs. If we pulled out a negative scalar from these terms, we would have a negative term, then a positive term, then a negative term, and that doesn't match up with what we have right here. So once again, just like with vector c, we can conclude immediately that vector d is not parallel to vector v. It's impossible for us to show that vector d is a scalar multiple of vector v, and so they don't have the same direction and therefore are not parallel. All right, and so that's it for this example, but I did want to give you an alternate way to go about this. If you have a hard time finding scalar multiples to pull out to show that your vectors are scalar multiples, another way that you could do this problem, although it might be a little bit longer, is to find a unit vector for each of these vectors. Because if a vector is parallel to another vector, both of those vectors will have the same unit vector. All right, so if you found a unit vector for vector v, you would want to see if any of these vectors have the same unit vector. And if you don't know what I'm talking about, don't worry, because the next example we're going to look at is how we find a unit vector in the same direction as a position vector. All right, so for this example, we want to find the unit vector in the direction of vector v, and vector v is equal to negative I plus 7j minus k, and then we want to find the unit vector in the opposite direction of v as well. All right, so we'll do each of these one at a time. Let's start with the unit vector in the same direction as vector v, and the formula that you need to know for this to find a unit vector in the same direction as some position vector, you want to take that position vector and divide it by its magnitude. All right, and remember when you denote a unit vector to use the hat or this caret instead of this standard vector notation here, okay? And so dividing a vector by its magnitude will give you its unit vector, which represents its direction. And so this is what I was talking about in the previous example. If you want to show that vectors are parallel, if you can find this unit vector for the vector in question and then find the unit vector for all of your other vectors, if those unit vectors are the same, that means that your vectors have the same direction and therefore are parallel. All right, so if their unit vectors don't match up, then you know that they're not parallel. Okay, so that's another way to do the previous example, but let's actually take a look at this one here. Let's actually work on this calculation. Note that you could also write this to be 1 divided by the magnitude of vector v multiplied by vector v. So this is just scalar multiplication of 1 divided by the magnitude times vector v. And so in order to do this, in order to find the unit vector in the same direction of vector v, we first need to find the magnitude of vector v. All right, and so remember, the magnitude of a vector is equal to the square root of the sum of the components squared. All right, now typically we look at a vector in this form where we have v1, v2, v3, and the magnitude of vector v would be equal to the square root of the sum of those components squared, right? We'd have v1 squared plus v2 squared plus v3 squared. But how do we go about this when our vector is in this form, in standard unit vector notation? Well, it's actually very simple. You just look at the coefficients of I, j, and k. The coefficient of I is -1, so that's going to be v1. The coefficient of j is 7, so that's going to be v2. And the coefficient of k is also -1, just like I, and so that will be v3 in our formula. All right, so the magnitude of vector v in this case will be equal to the square root of -1 squared plus 7 squared plus -1 squared. Okay, now -1 squared is 1, and 7 squared is 49. So this is equal to the square root of 1 plus 49 plus 1. And 1 plus 49 is 50, plus another 1 is 51. So what we find here is that the magnitude of our vector is equal to the square root of 51. All right, so to find our unit vector here, we will take 1 divided by the magnitude of vector v, which is the square root of 51, and multiply that by vector v. So we're going to be multiplying that by -I plus 7j minus k. And so if we multiply that through this quantity, multiply 1 divided by the square root of 51 by each of those terms, we will find that our unit vector is equal to -1 divided by the square root of 51 times I plus 7 divided by the square root of 51 times j minus 1 divided by the square root of 51 times k. All right, that is the unit vector in the same direction as vector v. And if you wanted to, you could check to make sure that that's true, that this is a unit vector. You could take the magnitude of this vector and it would be 1, right? That's what it means for a vector to be a unit vector. Its magnitude or its length is just 1. And so you could take the square root of the sum of these components squared and you should get 1. All right, but now we found the unit vector in the same direction of vector v, but how would we find the unit vector in the opposite direction of vector v? Well, it's actually pretty simple. We just take this unit vector that we already found and negate it. If you want to find a unit vector in the opposite direction of a vector, just find the unit vector and then make it negative. Because if you multiply a vector by -1, that just reverses its direction. So this was our unit vector that's in the same direction, but in the opposite direction, we will have that our unit vector is equal to these same terms, but negated. So we'll have +1 divided by the square root of 51 times I, minus 7 divided by the square root of 51 times j, plus 1 divided by the square root of 51 times k. Okay, it has the same terms or the same components, but now they're negated. This term was negative, now it's positive. This term was positive, now it's negative. This term was a negative, now it's positive. Okay, and just remember that this is not the only way to represent those vectors. You could also use your regular notation and have that this is equal to -1 divided by the square root of 51, comma 7 divided by the square root of 51, comma -1 divided by the square root of 51, right? You just take those coefficients of I, j, and k and make them the components of your vector because that's what they are. All right, and so you could do the same thing for this vector as well. I'll do that real quick. This is equal to 1 divided by the square root of 51, comma, -7 divided by the square root of 51, comma, 1 divided by the square root of 51. Okay, so you could also represent these vectors in this way if you wanted to, but both forms are correct answers for this problem. Let's take a look at another example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. All right, so next up, we want to find the vector v that has a magnitude of 3 in the same direction as vector w, which is equal to 3i minus j plus 8k. All right, now this seems like a complicated problem at first, right? Because what's the direction of vector W? We're not really told what that is, and so it seems a little bit confusing, right? How do we find a vector with a specific magnitude in the same direction as another vector? Let's break it down. When a problem asks you to find a vector in the same direction as another vector, what it's asking you to do is find a vector with the same unit vector as that vector. All right, because the direction of a vector is described by its unit vector. Okay, that's what a unit vector does. It has a magnitude of 1, sure, but what it really does is it tells you the direction of your vector. Okay, because if we look at our formula from earlier for our unit vector, remember that we said that a unit vector can be found by taking a vector and dividing it by its magnitude. If we were to solve for that position vector by multiplying both sides by the magnitude of the vector, we would find that the position vector is equal to its magnitude multiplied by the unit vector. The vector is defined by its magnitude multiplied by its direction. The unit vector gives you the direction of the vector, and the magnitude tells you how long that vector is, what its length is. So you multiply that length by the unit vector, and you have your position vector. So if we want to find a vector with a magnitude of 3 and the same direction as vector W, we need to know what that direction is. We know the magnitude is 3, but we need to multiply that magnitude by the direction of vector W, which is the unit vector that corresponds to vector W. All right, so I hope that makes sense. What we're going to do is find the unit vector corresponding to vector W, so we need to take vector W and divide it by its magnitude. All right, now the magnitude of vector W will be equal to the square root of the sum of its components squared. So we're going to take the coefficients of these three terms here, which are 3, -1, and 8. So we'll have 3 squared plus -1 squared plus 8 squared. And 3 squared is 9, -1 squared is +1, and 8 squared is 64. So this is equal to the square root of 9 plus 1 plus 64. Now 9 plus 1 is 10, plus 64 is 74, so the magnitude of vector W is the square root of 74. And that doesn't really simplify nicely. The square root of 74 doesn't have any factors that are perfect squares, so we're going to leave it in this form. But now what we want to do is find the unit vector associated with vector W by dividing it by that magnitude. So here's what we'll have. The unit vector will be equal to 1 divided by that magnitude of the square root of 74 times vector W, so we'll have 3i minus j plus 8k, all right? And that will give us 3 divided by the square root of 74 times I minus 1 divided by the square root of 74 times j plus 8 divided by the square root of 74 times k. And so this vector right here is the unit vector that describes the direction of vector W. So now what we can do, if we want to find vector V with a magnitude of 3 in the same direction as W, is take that direction, multiply it by the magnitude we want, and we'll have vector V. A vector is described by a magnitude and a direction, and so we have both the magnitude and the direction that we need to describe this vector. So let's do it. Vector V will be equal to that magnitude of 3 multiplied by this unit vector, and so we'll have 3 divided by the square root of 74i minus 1 divided by the square root of 74 times j plus 8 divided by the square root of 74 times k. And if we perform that scalar multiplication here of multiplying 3 through the terms of this unit vector, we'll have that this is equal to 9 divided by the square root of 74 times I minus 3 divided by the square root of 74 times j plus 24 divided by the square root of 74 times k, right? 3 times 3 is 9, 3 times 1 is 3, and 3 times 8 is 24. And so this right here is the vector, vector V, that has a magnitude of 3 and the same direction as vector W, okay? And once again, just like with our other examples, you could also express this vector in this form. You could have the component form of 9 divided by the square root of 74, comma, -3 divided by the square root of 74, comma, 24 divided by the square root of 74, and that's it. All right, so that would also be another way to write vector V. Okay, let's take a look at a different example. All right, so next up we're going to perform some vector operations for vectors in 3D. We have two vectors, vector V and vector U, and for those vectors we want to determine the following. we have the addition of the vectors, the subtraction of the vectors, where we're subtracting u from v, and then we're going to find the magnitude of 2 times vector v plus 4 times vector u, and then we're going to add the magnitudes of v and u. All right, so let's start with the first one here. We want to add vector v to vector u, and vector v is the position vector of the point -1, 6, -3, and vector u is equal to -2j plus 5k. All right, now before you do a problem like this, where you're given two vectors in two different notations, you should decide on one of those notations to use for the problem. I'll do a little mix of both here, but typically you want to choose one to work with, and that's it. That way you don't confuse yourself throughout the process, but I do want to show you the different ways that you could do this. And so just as a reference, vector v could also be rewritten as -I plus 6j minus 3k, right? -1 is our x component, so we multiply it by I. 6 is our y component, so we multiply it by j. And -3 is our z component, so we multiply it by k. All right, and then in the opposite way, we could represent vector u like this, 0, -2, 5. And that's because we don't have an I term, right? We just have a j term and a k term. So that means that I must be 0 if it's not there. So we have 0 for the x component, and then -2 for the y, and +5 for the z. All right, so keeping that in mind, let's do these operations. I'll start with vector v plus vector u, and I'm going to work with this notation first, and then when we do the subtraction, I'll use this notation, just so that you can see both of them. All right, but let's get started here. If we add vector v to vector u, what we have to do is add the x components, add the y components, and add the z components. All right, so that will look like this. Our resultant vector will have an x component of -1 plus 0, so -1 plus 0. Then we'll have a y component of 6 plus -2. So we'll write 6 plus -2. And then our z component will be -3 plus 5. So we'll have -3 plus 5. Okay, and so if we simplify, we will have -1, +4, +2. Right? -1 plus 0 is -1. 6 plus -2 is the same as 6 minus 2. So we have 4. And then -3 plus 5 is +2. And so that's one way that we could represent the resultant vector for this operation. But remember, you could also write it like this, -I plus 4j plus 2k. That would also be acceptable. You multiply the x component by I, the y component by j, and the z component by k, and add them together. But that's the resultant vector of vector v plus vector u. Now let's move on to the subtraction of vector u from vector v. To find the result of the subtraction of two vectors, we want to subtract the components of the second vector from the first. So we're going to be subtracting the components of u from the components of v. Now in this case, I'm actually not going to use this notation. Let's use our standard unit vector notation. And so here's what that looks like. We're going to have vector v, which is -I plus 6j minus 3k. That's this vector right here, which is the same as this vector. And then we're going to be subtracting vector u, which is -2j plus 5k. So the first thing that we want to do here is distribute this negative through these terms. So this will be equal to -I plus 6j minus 3k, but then we're going to distribute this negative through these two terms. So we'll have +2j, two negatives make a positive, and then -5k. So we'll have plus 2j and then minus 5k. And now all we have to do is combine our like terms. We add our I terms together, our j terms together, and our k terms together. It's the same thing as adding the x, y, and z components of our vectors together. So if we do that, this will be equal to -I, right? We only have one I term, so there's nothing to add to it. The x component of vector u is 0, so there's nothing to add. Then we'll add our j components. 6j plus 2j is 8j, so we'll have plus 8j. And then we'll add our k terms, so we have -3 and -5, which becomes -8, so we'll have minus 8k. And that is the resultant vector of vector v minus vector u. And once again, you could also write it this way. You could have -1, 8, -8, by taking the coefficients of those terms and making them the x, y, and z components. Okay, but now let's work on our next operation here. We want to find the resultant vector of 2 times vector v plus 4 times vector u. and then we want to take the magnitude of that vector. Okay, so let's work on that next. And before I get started here, if you're interested, see if you can pause the video and find this magnitude for yourself first. See if you can get the answer to this and then compare with the answer that I get. See if it's the same thing. You can also do that for this last part here. I think this one will be a little bit easier than this one, but regardless, I'm going to write out the solution to this one now. Let's work on finding this magnitude. First, we need to work on the scalar multiplication here, multiplying 2 by v and 4 by u. And I'm going to work with my vectors in the standard unit vector notation. So we're going to have 2 times vector v, which is right here. So we have negative I plus 6j minus 3k. And then we're adding that to 4 times vector u, which is negative 2j plus 5k. All right, so now all we have to do to perform this scalar multiplication is multiply those scalars through these quantities. So this will be equal to negative 2i plus 12j minus 6k, and then we're adding that to negative 8j plus 20k. All right, so 2 times negative 1, negative 2, 2 times 6 is 12, 2 times negative 3 is negative 6, 4 times negative 2 is negative 8, and 4 times 5 is 20. Okay, so now we just need to add our like components, and I just realized that I forgot to write our magnitude bars, right? We need to take the magnitude of this vector. Don't forget that. That's an important part of this problem. But anyway, if we add our like terms, our I terms, j terms, and k terms, this will be equal to the magnitude of negative 2i, right? We don't have another I term, just this one. And then we have 12j and negative 8j. That will become positive 4j, right? 12 minus 8 is 4. And then for our k terms, we have negative 6k and positive 20k, and 20 minus 6 is 14, so we'll have plus 14k. All right, now to take the magnitude of this resulting vector with components negative 2, 4, and 14, we just need to take the square root of the sum of those components squared. So this will be equal to the square root of negative 2 squared plus 4 squared plus 14 squared. Now I'm running out of space here, but I'll simplify up here. That'll be equal to the square root of 4 plus 16 plus 196, right? Negative 2 squared is 4, 4 squared is 16, and 14 squared is 196, all right? So now if we simplify, 4 plus 16 is 20, plus 196 gives you 216. So this is equal to the square root of 216, but 216 does have a factor that is a perfect square. It's divisible by 36. So you could rewrite this to be the square root of 36 times 6. 36 times 6 is 212, and the square root of 36 is 6. And so I'm just going to erase this arrow real quick so I have some space. This will be equal to 6 times the square root of 6. And so 6 square roots of 6 is the magnitude of the addition of 2v and 4u. All right, let's work on our final computation here. Lastly, we want to add the magnitude of vector v to the magnitude of vector u. So let's start by calculating each of those individually. The magnitude of vector v will be equal to the square root of the sum of the components squared. So we'll have the square root of negative 1 squared plus 6 squared plus negative 3 squared. And then we're going to add that to the magnitude of vector u, which will be the square root of its components squared. So we'll have 0 squared, which is 0. But then the other two will have negative 2 squared plus 5 squared. All right, now negative 1 squared is 1, 6 squared is 36, and negative 3 squared is 9. So this is equal to the square root of 1 plus 36 plus 9. And then we're adding that to the square root of 4 plus 25, right? Negative 2 squared is 4, 5 squared is 25. So we have 4 plus 25. Now, 1 plus 9 is 10, plus 36 is 46. The square root of 46 doesn't really simplify any further, so this is just going to be equal to the square root of 46, and then we'll add that to this square root, which is the square root of 4 plus 25, which is 29, and so we have the square root of 29 for the magnitude of vector u. All right, and so at this point, there's nothing else we can really do to simplify this. These don't really add together nicely. So you could say that the square root of 46 plus the square root of 29 is the final answer here. But if you want to know approximately what that's equal to, you could also plug it into a calculator and find that it's approximately equal to 12.167 and some more decimals. All right, so that's approximately what the square root of 46 plus the square root of 29 would be, which would be the final answer for this last part of this example, which was the addition of the magnitude of vector v and the magnitude of vector u. Okay, let's take a look at one more example for this video. All right, so here's our last example. We want to use vectors to determine if the points below are collinear, which essentially means do they lie along the same line? All right, so visually that looks like this. If 3 points are collinear, then that means if you have a line, all 3 of those points would be along that line. All right, there only has to be one of these lines, right? There only has to be one line that passes through all 3 of those points, but that line does have to exist for those points to be collinear. If you can't draw a straight line through all 3 of them, then they're not collinear. Okay, and so this is a little bit of a weird problem because how do we use vectors to show that this would be true for these 3 points? How do we know if these 3 points lie along the same line? Well, to help you think about it, let's label our points. This will be point A, this will be point B, and this will be point C. If these 3 points are collinear, then these 3 points could be A, B, and C, right? So if this is A, this is B, and this is C, what would you say needs to be true about these 3 points regarding vectors if these points lie along the same line? Well, here's what would need to be true. In order for these 3 points to lie along the same line, the vector from point A to point B would need to be parallel to the vector from point A to point C, right? I didn't draw it over top of the other one, but imagine that they are both along that same line and they're parallel. If we can show that the vector connecting point A to point B is parallel to the vector connecting point A and point C, then we have no choice but to conclude that these 3 points are collinear, that they lie along the same line. All right, I hope that makes sense because if vector AB is not parallel to vector AC, then that means that this vector is pointing in some other direction, so we couldn't draw a straight line through all 3 points. We would have to draw a curved line to connect them all, which is not the definition of collinear. We want to be able to draw a straight line through all 3 points, and in order for that to be true, vectors AB and vectors AC need to be parallel. Okay, so let's see if that's true for these points. We're going to look at vector AB. We want to figure out what that's equal to. And we want to look at vector AC. We want to determine what that's equal to as well. And if we can show that those 2 vectors are parallel, and that can be by finding a unit vector or showing that they're scalar multiples, then we can conclude that our points are collinear. Okay, but first we actually need to find these vectors. So we're going to need to find position vectors by taking the difference of our x coordinates, y coordinates, and z coordinates for our points. All right, so for vector AB, the terminal point is point B and the initial point is point A. So we're going to be subtracting the coordinates of point A from the coordinates of point B. Okay, so for the x component, we'll have 3 minus 0, which is 3. So I'm just going to write 3. For the y component, we'll have 4 minus negative 2. So 4 minus negative 2. Then for the z component, we'll have 4 minus negative 5. So 4 minus negative 5. All right, now let's work on AC as well. For vector AC, A is still the initial point, but now C is the terminal point. So we're going to be subtracting the coordinates of A from C. So we'll take 2 minus 0 for the x component. So we'll have 2, and then 2 minus negative 2 for the y component. So we'll have 2 minus negative 2, and then 1 minus negative 5 for the z component. So we'll have 1 minus negative 5. All right, now let's simplify. This will be equal to the position vector of the point 3, 6, 9, right? We have 3, and then 4 minus negative 2 is the same as 4 plus 2, so that's 6. And 4 minus negative 5 is the same as 4 plus 5, which is 9. Okay, so that was vector AB. Now for vector AC, this will be equal to 2, 4, 6, right? We have 2, and then 2 minus negative 2 is the same as 2 plus 2, which is 4, and then 1 minus negative 5 is the same as 1 plus 5, so we have 6. And now upon first glance, it doesn't look like these vectors are the same, right? They don't look like scalar multiples, but watch what happens if we pull out some common factors. Notice that for vector AB, each of these components are divisible by 3, and so if we pull that 3 out, this would be equal to 3 times 1, 2, 3, right? 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. In the same way, each of these components are divisible by 2. So if we pull that 2 out, we'll have 2 times 1, 2, 3, right? 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. And so what we're left with are two vectors that are equal to some scalar multiple multiplied by the same vector, the position vector of 1, 2, 3, right? These two vectors are the same. They're just being multiplied by different scalar multiples, which means that these vectors are scalar multiples. They have the same direction. And so therefore, they are parallel to each other. All right, so we have shown that vector AB is parallel to vector AC. And because of that, that means that these 3 points are collinear. All right, so we can make the conclusion that the points are collinear. Okay? And so with that, that is it for this example. And this was the last example for this video. But if you do want to see some more examples, I have more available on my membership site. So feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.